Hello everyone. In the previous video we have seen depth first search and depth limited search. Both had advantage of less memory requirement, although both the algorithms are not complete and also not optimal. In this video we are going to discuss a new algorithm called as iterative deepening depth first search, or shortly iterative deepening search, IDS. This attempt to get back the advantage of completeness which was there earlier in breadth first search. In a way, it is going to get advantages of both breadth first search and depth first search, and it also comes at a certain cost. Let's see what is the cost. So IDDEFS finds the best depth limit. So we have seen in depth limited search that we are going to set a random or a particular limit value until which a particular node would be going deeper. Beyond that limit, it doesn't goes. It assumes that there are no more nodes after the leaf node in depth limited search. Whereas in IDDEFS, it finds the best depth limit. We are not going to fix the limit. We are going to slowly increment that limit and thereby get the advantages of BFS and DFS. So it does this gradually by increasing the limit. So first we will only be having depth 0, and then we will increase depth 1, depth 2, and so on until a goal node is found. But one of the main disadvantage, although it is not so big a disadvantage, is that there is a repetition. So when we search node with various limits, we are doing multiple times passing through the same nodes. We'll see that with an example. So basically, iterative deepening combines the benefits of both breadth first search and depth first search. Like DFS, it has modest memory requirements, which is order of BD, and like BFS, it is complete. So when the branching factor is finite, and optimal when the path cost is a non-decreasing function of the depth of the node. So it is achieving what a BFS algorithm is has achieved, which is completeness and optimality. Whereas it is also having the advantage of DFS, which is the requirement of less memory. So the only one limitation, although it is not so important, is there is a repetition in the way the nodes are being generated. So but it is not too costly, because the nodes which are there in the top layers are not going to be repeated many times. Nodes which are going to be there in the bottom layer are not going to be repeated many times. Only the nodes which are there in the top layers are going to be repeated. So in an asymptotic sense, it does not affect much in terms of complexity. So let's take an example and analyze this. Consider this tree where A is the initial node and Q is the goal node. So iterative deepening works as follows. First we'll assume limit as 0, so only node A is generated. Then limit as 1, then we have A, B, C, D. So it is like a DLS algorithm, depth limited search algorithm, with increasing limit value. So next we take limit is equal to 2. So our traversal would be A, B, E, F, C, G, D, H. And then once again, if we increase depth to 3, it traverses A, B, E, I, F, J, K, and so on. So that's what clearly we can see. Once the depth is 4, we will be reaching to the goal node, and that's when the traversal will stop. So let's see how the algorithm of iterative deepening depth first search looks like. So it can be very easily implementable using the DLS algorithm, depth limited search. In the depth limited search, we had a particular limit value, whereas here we are keep on increasing the limit value starting from 0 to infinite. So until we reach to a state where we find the goal node. So as you can see here, we have DFS algorithm, DLS algorithm. So the first two, the orange color box function, which is depth limiter search, and the pink color function, which is recursive DLS. We have these both are we have seen in depth limited search. So the new thing which we are seeing is this blue box where we have iterative deepening search, where we run a for loop from depth values ranging from 0 to infinite, and we call depth limited search multiple times until we find the result. So that's how it works. So if we see the time complexity once again for iterative deepening depth first search, we are not having a too much of cost by having multiple times, by traversing multiple times, because the traversal is only happening in the top, and the number of nodes in the top are generally less as compared to the nodes which are there in the bottom of the tree. So therefore it is not a too much of a cost which we are paying for the advantages iterative for iterative deepening depth first search is providing. So if you want to calculate the total number of nodes generated in worst case, it would be something like this. So we have D levels and B is the branching factor, and so each of these we are getting. So let's derive these, how we are getting this particular expression. Consider a node A and B, C, D, and assume you have few more nodes E, say F. So as you can see, in depth iterative deepening DFS, we start with A, so when the limit is 0. So as you can see, this for loop runs from depth value 0. When depth is 0, we have only A node which has been generated. When depth is 1, it generates A, B, C, D. So this A node is being generated once again. So when depth is 2, once again we are generating A, B, but not C. We will be going deeper, E, and then we have F, and then we have C and D. So each time we are repeating these nodes. And how many times this node A is being repeated? It is being repeated until we reach D times. We are repeating it D times. So this expression of having D into B comes due to that. Okay, so B is the branching factor. So we have 3 branches here, B, C, D, and this is being repeated D times. And next time we will be having, so the E and F will be repeated only D minus 1 times, and so on until the last node. When we reach to the last leaf node, we will only be repeating 1 time, but we have B power D nodes. Okay, because in the last layer, when you have in the last layer, for example, as we saw here, so this consider in this tree. So if it is last layer, it is going to pass through all these nodes in a DLS fashion, and it have a complexity of order of B power D. So therefore, so we have complexity of order of B power D. So why we are saying it is not so complex? Because asymptotically, which means that when we are doing for a large case, BFS and DFS would be very similar. When the tree is very big, B power D, the last expression, will be way larger as compared to the first few expressions. So therefore, BFS, iterative deepening depth first search, converges to BFS in terms of time complexity. So if you want to calculate how many nodes we are going to have, IDDFS, is going to have 1, 2, 3, 4, 5, 0 for B is equal to 10 and D equal to 5. And for N is equal to BFS, we are going to have this expression. So 10 plus 100 plus 1000 plus 10,000 plus 1 lakh. So iterative deepening is the preferred uninformed search method when the search space is large and depth of the solution is not known. So that's one of the important conclusion we are getting from the uninformed search algorithms. So whenever the search space is large, IDDFS will be beneficial. So if you see the time complexity of iterative deepening compared with other algorithms, it is complete algorithm, it is optimal, and it has a time complexity of order of B power D and the space complexity of order of BD. So it is getting the advantages from both BFS and DFS. So now let us see one other algorithm which has a reduction in the time complexity from order of B power D to order of B power D by 2, but it also comes with a little increase in the substantial increase in the space complexity, which is order of B power D by 2. So this is called as bidirectional algorithm. So the idea here is to simultaneously start from the initial node and also the goal node and find out a point where you will meet in the middle. So both, once you start from the initial node, you will be keep on generating the child nodes. The same thing we do from the goal node, and we generate the child nodes in the reverse order. There would be a space where the two frontiers intersect, and we will have a solution, a common solution, and that solution will have, in reaching that solution, the time complexity and space complexity are very less. So as compared to the traditional algorithms or the earlier algorithms has order of B power T, whereas here we will be only have B power D by 2. So space complexity, because it is going to follow the breadth first search, which means we are going to store all the nodes in the memory, and we are not traversing the whole depth D, we are only traversing the half of the depth D. So we will be having a same space complexity also as order of B power D by 2. So both time and space complexity are order of B power D by 2 in bidirectional search. So that is, space requirement is one of the weakness in bidirectional search. So this is how it looks like. So you have a root node, you have a goal node, you traverse both by generating the child nodes, and you will reach to a point in the middle where they intersect, and that's where you conclude if there is a common search point, common node when you between both the frontiers, then you can say that you can have a path from initial node to the goal node. So once again, the time complexity is order of B power D by 2 and the space complexity is order of B power D by 2. So all these search algorithms are uninformed search algorithms. So they vary in the approach. So BFS has completeness and optimality at the cost of huge memory requirement, and uniform cost search works when the edge costs are not same and we want to find a shortest path from one particular node, initial node, to the goal node, but the complexity wise they are higher. Both DFS, DLS are not complete and not optimal. Not complete, especially in the infinite spaces, but they have the advantage of requiring the less memory space. Iterative deepening has less memory space. It gets the advantage of both BFS and DFS. So with similar to BFS, it has completeness and optimality, and similar to DFS and DLS, it has a lesser requirement of memory. Bidirectional search has further lesser requirement in time complexity, but at the cost of an increase in the space complexity. So this is the summary of all uninformed search algorithms.